Hello, welcome back. So we have been talking about the electric field and the electric flux density, which is related, and Gauss's law and how to efficiently calculate these things for symmetrical problems. But really, in engineering, we can't really do anything useful with anything until we can analyze how much work and how much energy a system has. This goes for any engineering subject. You need to be able to do work. You need to be able to communicate with the physical outside world. So if these electric fields that we've been discussing have no energy in them or have no, there's no work associated with them, then we wouldn't be able to apply these things anywhere. So in this video, we're going to examine, or begin to examine anyway, the work and the energy that, in particular, we're talking about static electric fields have. Now, let's review some concepts from physics. So in this top picture, I've got the gravitational field in red that points towards the ground. I've got a mass, m, that's moving from a height y equals a to a height y equals b, which is lower than a, and we're calling that displacement vector then L. And why does the mass move? Well, it moves because of the force, it accelerates actually because of the force F due to the gravitational field G. So as mass m falls from height y equals a to height y equals b, the field G does positive work. That's going to be key here. And why is it positive work? That's because the gravitational force F is in the direction of the displacement L. F and L are in the same direction, right? So that's positive work by the field. F and L mean the work is positive by the field. All right, now let's consider a related but slightly more complex system below that, where we have A now and B related to this incline on a ramp. As mass m falls from A to B on the incline, it's the component parallel to L that does the work. We just said that F and L do positive work because they're in the same direction. So now L is down the incline of the ramp. F, the gravitational force, points straight down, but it has a component that's parallel to L and that's perpendicular to L, right? The component that's parallel to L does the work, just like up here, F was parallel to L. The part that's perpendicular to L actually does no work. This should not be surprising. This was covered in physics. So in general, the work done on the mass by the field, I'm going to write that down, on mass by the field. I'm going to try to emphasize on and by, is the following. The work is equal to the magnitude of F times the magnitude of L. And then remember we said it's only the component that's parallel, so that's key here for a dot product. That should not be surprising. So we need the cosine of the angle in between, which is of course the dot product. So that's F dot L, and that is the work. Okay, so now if we talked about an external agent, maybe you wanted to lift something up, the work done or the energy required, remember work and energy are related, they're the same, the work done or the energy required to move m against the field, move m against, spelled against wrong there, against the field. Because of energy conservation principles, that work is negative F dot dl. So this is going against the field. Now, if either F or L is curved, L being curved is simple to understand. You just have a curved path, not a straight path. But F being curved would mean that the applied force, the direction of the applied force varies as the mass moves. If one or the other or both is curved, then what we have to do is consider short, straight segments, infinitesimally thin segments, right, of the path. And then we consider the differential work required against the field. So if you're moving against the field in something other than a straight path, or when F is changing, we have to say that that differential work is negative F dot dl, like this. And then the total work required in moving M is the following: negative integral F dot dl. So this would be the initial, and this would be the final. Now your book uses, unfortunately, A and B, or it's common to write A and B here. So now we're talking against the field. So in my drawing, this would be A now, and this would be B. See, the perspective changes. Are you talking about on the mass by the field, or are you talking about against the field, by an external agent? So this is the work done by an external agent, negative integral A to B F dot dl. This is a line integral which we've discussed earlier in the semester. Now suppose the field is an electric field, right? I mean, we're not talking about gravity here. And the force due to the field then is the electric force. Since F is equal to Q times E, the work required to move Q from A to B by an external agent is negative Q times the integral from A to B of E dot dl. The analogy here is perfect. Moving mass in the gravitational field is like charge in an electric field. The gravitational field is like the electric field, and the gravitational force, or the weight, is like the electric force. The analogy is perfect. So now here is the work required to move by an external agent the charge Q inside an electric field. It depends on Q. The stronger Q is, the higher Q is, then the more work possibly, right? Just like here in the gravitational field, the heavier something is, the more massive it is, then the more energy or the more work you have to expend to lift something up. Sometimes, or usually, it's instead of talking about work in electricity, what we talk about is work per charge. Work per charge. So that we normalize the work to take this Q out of the equation and talk about work per charge. In that case, we use the letter V sub AB. So again, this is W per charge. Joules per coulomb is then just equal to negative A to B E dot dl, like this. VAB is called the potential difference between points A and B. A is, like we said, the initial point, and B is the final point. Now, if VAB is less than 0, so we're talking about like a negative normalized work, basically normalized work, there is a loss in energy, and the field did work. Field did the work. Remember, this V or this W is the work done by an external agent. So if you find that that's negative, well, it wasn't the external agent that did the work. It was the field that did the work. So in this case, this you would find would be negative work because it's the field that's doing the work. You're not lifting something down. That doesn't make any sense, right? Now, then alternatively, if we find that VAB is positive, then there is a gain in energy, and the external agent did the work. So this would be like in the gravitational field, if you picked something up off the ground, you're the external agent, you're doing the work, not gravity in that case, and the thing is gaining work, gaining energy, potential energy. And of course, VAB is measured in joules per coulomb, and we call 1 joule per 1 coulomb a volt, 1 volt. All right, I'm going to erase a lot of this now. Now, as we showed, the electric field, we're going to bring in the electric field and we're going to see the relationship between the electric field and the potential difference. We showed that the electric field due to a point charge Q at the origin, this is like the 5th time this thing is coming up, Q over 4 pi epsilon 0 r squared AR, right? So now let's calculate the voltage, not the voltage, excuse me, the potential difference from some point that's a distance away from the origin to some distance b away from the origin. So we would say q dot, not q, e dot dl. And when I dot with dl, I only need the radial component of my path, because the phi component and the theta component, when dotted with e here, will be 0. So I do this dot product, and then I do the integration. 1 over r, integrating 1 over r squared is negative 1 over r. And so what I get is this here. The negative goes away because of the integration of r to the minus 2. This is the potential difference, right, between points A and B when we have a point charge at the origin. Now, if we let VA, or call VA to be Q over 4 pi epsilon RA, and similarly VB with RB, then what we've got here, we're going to call these the potentials at A and at B. So then VAB is the potential at B minus the potential at A. Only at infinity is the potential absolutely 0, because if I plug in a radius of infinity, then 1 over infinity is 0. But anything else, I have a finite potential. So you see, the potential difference here is relative. The potential difference, or the potential at B, is relative to A, and so forth. So sometimes we set this reference point at infinity because the potential is absolutely 0 there. So if we let RA go to infinity, and then we're just going to call RB just R, then we can drop the subscripts. So the potential then we would say is 4 pi epsilon 0 r. That's due to a point charge. Take the charge divided by 4 pi epsilon 0 and the distance away. Notice it's a scalar, right? It's not a vector. So to some degree, then, working with potentials is simpler. It's easier to work with them compared to electric fields. And again, I want to make it clear, this is with a point charge and we're saying the voltage at infinity is 0. Now the same, or I guess before that, if a point charge is not located at the origin, so this was a point charge at the origin, but instead is at a position vector r prime, then the potential at position r is given by this thing here, V equals Q over 4 pi epsilon 0, and then we take the difference, unsurprisingly. So this thing is the length of the difference between where your charge is and at which point in the space you're considering the potential to be. Okay, so you just take that difference, and then of course if r prime, the distance vector of the charge, is 0, that is if it's at the origin, then it reduces down to this equation. So this is the general equation. Again, r prime is the location of charge Q. R is the field point. At which point in space do you want to know the voltage? Or the potential difference, excuse me. Also, the same tricks apply as did with electric fields. So superposition is the big one. Superposition means that you can add the potentials together. So this was due to one charge Q, and if I have a couple charges right in space, I can find the voltage or the potential difference at one point, or at a point due to one charge, then find it at that same point due to another charge, and then add them up. That's superposition. And then if we had a continuous distribution, then we would integrate over the continuous charge the charge distribution to get the potential difference. Now, since VAB is equal to VA minus VB, do I have a, no, whoops. That's, excuse me, that should be VB minus VA. VAB is equal to VB minus VA. Notice that's equal to V minus VBA, like that, which would be minus VA minus VB, right? So these two things are equal, VAB minus VBA. So if I took VAB plus VBA, well, that would be going around in a path then in the electric field. That would be a closed path. So I could express that like this. That must be 0, and it's 0 because VAB plus plus VBA, they're opposites of one another, so they add to 0. So what we're saying here is that I've got an electric field. Here's my electric field in space, E. And if I wanted, here's A, here's B. If I traveled like this, any closed path, the change in voltage, as long as I start in the same spot that I finish, right, the change in voltage is 0. And from Stokes' theorem, which relates a closed line integral with a surface integral, right, like this, using the curl, the only way for this to be 0 is that the curl of E is equal to 0. Nice. So a static electric field, its curl is always equal to 0. This is another one, a second of Maxwell's equations. This is the integral form. This is what's called the point form. Point form. So that's the second of our Maxwell's equations. Interesting. So let's think of some of the consequences of this equation. And let's apply it to circuits. Let's say I have some circuit here. This is V2. Maybe there's a potential difference here, V1, potential difference here, V2, potential difference here, V3, like that. Well, what we just said was that if I go around any closed path, then the voltages should add to 0. So let's do that. So for example, there are 3 closed paths here. There's the 2 inner rectangles and then there's the outer rectangle. Let's go to the left inner rectangle. If I drop by, I can't call that V1. Let's call this VS1 and call this VS2. So if I drop by V1 and then I drop by V2 and then I increase by VS1, that must be equal to 0. This is what you call Kirchhoff's voltage law in circuit analysis. And you could make the same argument around this loop or the outermost loop. But that's due to one of Maxwell's equations, and it's this guy here. Now, a vector field that satisfies this, and remember this was called the circulation of E around L, or the curl is equal to 0. We say that that vector field is conservative. That's a conservative field. So that means that the path taken to get from A to B does not matter. The work done is the same. The net work is the same. It does not matter how you get from A to B. Gravity is also a conservative field, just like the electric field is. So if you were to raise a mass from the ground to a certain height, it doesn't matter if you raise it, and then you raise it half as much, and then you shift it. Here, let me draw a picture. It doesn't matter if you raise it directly, like this, or maybe you raise it a little bit and then move it over here, and then move it up like that. You've done the same net work in both cases because gravity is a conservative field. All right, very good. And then finally, there's a lot to cover in this video. I want to show you the relationship between E and V. Right, we've been talking about the electric field. Now in this video we introduce the potential difference. We said, of course, that the potential difference is negative integral E dot dl. And so if I differentiate both sides, this means that the dV is equal to negative E dot dl. Okay, and we'll say that E will work in rectangular coordinates and say that E has an x component, a y component, and a z component. So this is Ex dx minus Ey dy minus Ez dz. Now from calculus, you know that the total change is the sum of the partial changes. That is to say, dV, which is the total change, is the sum of the partial with respect to x times dx plus the partial with respect to y times dy plus the partial with respect to z times dz. Now if we compare these two things, right, dV is equal to this thing, then we see that Ex is equal to negative dV dx. EY is equal to negative dV dy. EZ is negative dV dz. So what does that mean? Well, and here's the punchline. The electric field is the negative of the gradient of V. Awesome, right? Exclamation points. E is the negative gradient of V. So everything that we said about the gradient is still applying here, right? So, for example, the direction of E is opposite. It's opposite the max increase in V, right? The gradient gives you the direction of max increase. So E is the opposite of the direction of the max increase, opposite because of the negative sign. All right, so that's it for now. Thank you.